So good morning, everyone. My name is Julio. I made this work when I was at the Federal University of Rio de Janeiro in Brazil. I made this work with Professors Landesman and Ribeiro, and the title of this work is Interface Model to Fire-Thermo-Mechanical Performance-Based Analysis of Structures under Fire Conditions. So traditionally, the behavior of structures under fire conditions has been achieved by prescriptive simplified procedures widely available at international codes and standards like AISC or Eurocodes. Those codes are generally focused and check if isolated members could meet the required fire resistance time. Nowadays, advanced numerical models based on finite element method can provide global behavior of structures, including large displacements, second-order effects like catenary or membrane. However, the application of these models to fire conditions is generally related to simplified representations of the thermal exposure conditions, generally temperature time curves like presented on Eurocode or AISC, the ISO 834 or hydrocarbon curves or parametric curves. And we need to establish that those curves do not represent accurately the fire development or the temperature distribution inside a compartment. On the other hand, we have another advanced numerical models based on computational fluid dynamics. They're capable to solve analysis of systems involving fluid flow, heat transfer by means of a computer-based simulation. Those models can provide a reliable description of fire evolution, just like FTS. We can have like the gas temperature distribution, the velocity field, the chemical species. But even with all the efforts related to develop each side separately, a coupled fire-thermo-mechanical analysis is a relatively new area of research. This coupling is not a trivial. We have a lot of intrinsic differences between those two models, like algorithms, timescales, mesh sizes, which make this an encouraging task. So the main goal of this work is create a fire-thermo-mechanical interface model to handle this performance-based analysis of structures under fire. Now we have two separate universes. They are pretty established by themselves, but we need to create a bridge to connect these two worlds to use the best of each universe. So this work is intended to create an automated code that will improve the reach of fire engineering, allowing the simulation of the behavior of global structures, not just isolated members. The structures could be discretized with shell or solid elements or both. The fire simulation will be handled by a computational fluid dynamics, and the thermomechanical or the thermal and mechanical simulations will be handled by the finite element method. The main goal here is to create an interface, a bridge between these two universes. Right now, this interface is running between Fire Dynamics Simulator and ANSYS, but the methodology can be applied to any other codes. In this presentation, I will start by the methodology when I explain how we calculate the surface thermal exposure, then how to handle models with geometries that do not match perfectly, and how to input the heat flux into the finite element method models. I have two applications here. The first one is intended to verify this interface, and the second one is application of H profile column. At the end of the presentation, I have some conclusions. So this fire-thermo-mechanical model is related to a domain that will include the structure itself and its components, from where we have mechanical loads and the thermal conduction, combined by the surroundings when we have flame and hot gases dynamics. Unfortunately, this couple fluid-solid problems will need distinct techniques to address all the physical phenomena involved. So this methodology decomposes this domain into two parts. The first domain is devoted to fire simulation when all the structure is simplified, and we include the surroundings when we have the flame and hot gases dynamics. The second domain related to the thermomechanical behavior when we just have the structure. So to create a bridge between these two universes, we need to characterize the thermal exposure of the surface and create a boundary condition for the thermomechanical model. That's what we're trying to do here. So heat can be transferred from flames and hot gases to surfaces of structures by radiation and convection. So this total heat flux can be obtained by the sum of these two parcels. The convective heat flux can be obtained by Newton-Coulomb law, which is a scalar heat transfer coefficient multiplied by the difference of the temperature around the surface and the surface temperature. The radiative heat flux is a little bit more complex. It will be calculated by a radiative energy balance, which means the absorbed energy minus the emitted energy by the surface. The absorbed energy will be considered as part of the incident energy. Part of this incident energy will be reflected, so it will be discarded from here, and part will be absorbed. This absorbed part can be calculated just multiplying a factor by the incident heat flux. This variable is known as absorptivity. The emitted part of radiative heat flux is calculated by Stefan-Boltzmann law, which is emissivity times Stefan-Boltzmann constant times the temperature of the surface in Kelvin at the fourth power. If we put these two inside this first equation, we will have this form. If we remind that according to Kirchhoff's law, absorptivity and emissivity are the same, we can write the radiative heat flux at this form. Remember, summing those two parcels, we have the total heat flux. Unfortunately, even advanced fire simulation models like FDS are not capable to calculate accurately the temperature distribution of solids. So that's why it's hard to transfer just the total heat flux, and we will need another special treatment on the surface to transpose this barrier. In this methodology, we use a diabatic surface temperature concept, which says that we can replace the exposed surface by an ideal surface exposed to the same heating conditions. The heat flux to this ideal surface will be by definition 0, and we can calculate the adiabatic surface temperature inside of a fire simulation. And this variable is known by being capable of combining the complexity of the fire models into a scalar variable. But how to transfer this variable to a finite element method? What we're going to do with that? This is not the surface temperature that we need. So if we remember that the ideal surface and the exposed surface are exposed to the same heating conditions, we can solve these equations as a system, and this definition of the total heat flux can be applied at the finite element method. We need to transfer the adiabatic surface temperature, and we will have the surface temperature calculated at each time step in the finite element method. This specific methodology considers that we need to include the heat transfer coefficient to solve this equation in a correct, better way. These two variables will be denominated here as surface's thermal exposure. So now that we know the variables that we're going to transfer, we need to know how to handle this transfer. To handle with geometries that do not match perfectly, even if you're trying to build a model with the same element size to achieve a good result in the thermomechanical model, will lead to small elements and maybe an unfeasible CFD model. So we need to find a way to map this geometry against this one. So this connection will be handled by a collection of I key points. Each exposed face will have an I key point with coordinates x and normal n. And we create a code called FDS to FTMI, which basically will track down every exposed face, calculate all the E key points, go to the CFD available results inside of a boundary file, and get the closest available results for adiabatic surface temperature and heat transfer coefficient. After that, we will have a script written in APDL language that will make ANSYS run the simulation with the correct boundary conditions. To apply this heat flux inside of ANSYS, we will use this element. It's a surface effect element called SURF 152. To calculate the heat flux using this element, we need to prescribe the adiabatic surface temperature at this extra node, and the heat transfer coefficient will be a property of the surface. After that, the model will calculate this total heat flux by that equation, and we create vectors at the nodes using the area of elements, number of nodes, and the normal direction. So now we can have the results from FTS, we can iterate them, get the results, and apply at a thermomechanical simulation. I'll present two applications. The first one is intended to verify this interface. It's a simple steel panel that is exposed to a localized fire. We are trying to analyze the effects of the simplifications related to calculate this heat flux by adiabatic surface temperature and heat transfer coefficient, and if our mapping tool is working well. This fire simulation domain is 1.5 for 1.5 for 2 meters high. And this first scenario is a leakage of 0.1 liters per minute of methane at a velocity of 2 meters per second. This leakage is in the ground 30 centimeters from the panel. So this panel is parallel to the Cartesian axis, which will make possible to use the one-dimensional conduction model inside FTS. The main target here is to verify FTMI, and we will do that comparing the temperature distribution obtained by FTMI and ANSYS. FTMI and FTS, sorry. For this example, we need to adapt our thermal model to just consider the heat conduction at the X direction. By that means, we keep the comparison at the level of the interface. We are using a thermal model similar to what FDS has, a one-directional heat conduction model. That's the adiabatic surface temperature distribution with 5 minutes of fire-lapsed time. We can see a radial pattern. That is, the center is not circle, it's not a circle because of the flame shape. And if we look at the temperature results, we can see that the maximum difference is about 0.5%, which we consider as a great correlation. So by that result, we can say that FDS is capable to process the surface's heat condition accurately. We could prescribe this and have the results from a finite element method model. After that, someone can make a logical exercise and ask about a need for a complex methodology like that to achieve the same temperature profile already provided by FTS. But we need to keep in mind that we needed to adapt our thermal model to have the same condition of the FTS. In this steel panel, using a three-dimensional thermal model, we can see that we have a lot of heat spreading on the panel surface. If we use FTMI in full mode with three-dimensional thermal model, we will have a maximum temperature of 154 C, which is only 85% of the maximum temperature obtained by the previous model and FTS, which is 181.5. So even with the same boundary conditions, now with the three-dimensional thermal model, we have a lot of heat spread over the panel surface. In this study, this plane surface is aligned with Cartesian axis, but generally the structure geometries are very complex. And even for simple panels like that, they usually have stiffeners or adjacent structure that will change this heat conduction field. That's why we need a complex geometry like that, a complex methodology like that. The second application case is an H-profile column. We have a simple supported H-profile column. This column is 3 meters high. This cross-section is about 30 centimeters of the flange and 40 centimeters in the web. The first scenario is a 200 megawatt pool fire, 20 for 20 centimeters. The center of the pool fire is 40 centimeters from the web. This column is subjected to a vertical load which corresponds only to 1/50 of the Euler-Buckling critical load. By that, we want to have close to a uniform stress distribution in the column, and all the horizontal displacement will be generated due to thermal gradient. We are away far from the buckling behavior of this column. Another interesting feature about this example is that each side of now shell elements will have a different thermal exposure. We can call that like a shadow effect. So as this part of the column will be facing the fire, the exposure of the surface will be different from that parts like this side that are not facing the fire. And we need to account that to have a better thermal gradient. As I said before, all the bending moment that we have in this column will be generated by the thermal gradient. So that need to be accurately accounted. The maximum temperature achieved here after the application of FTMI is at points A and D, for example, that are close to the fire source. We have a different, A1 means the surface that is facing the fire, and the subscript 2, the faces that are facing the other side. So we have a difference for around 5 Celsius degrees here and 6 Celsius degrees for point D. Point B and A are far away from the fire, and they will be affected by the conduction process, as we can see here. This difference in temperature, as we can see in this flange, we have higher temperatures in this side and cooler temperatures here. This difference of temperature will make this part expand more and will create that bending moment I was talking before. Now we have the stress, von Mises stress distribution around here, and we can say that at the beginning of the fire we have a stress state close to a uniform state, and with the expansion of the heated parts of the flange we have this bending moment here. The formations are amplified 15 times, so we can see all this generated bending. As the temperatures got higher, our material are changing. We will have a reduction of the yield strength. We will have variation of the elastic modulus. So our model are accounting that, so we can see that with the time is passing, we will have lower stress because the material properties have changed and amplified deformations. Looking at the displacements, at the top of this column, we have a displacement around 7 millimeters, even with the vertical load creating a negative vertical displacement at the beginning. The horizontal displacements generated at point A and D are about 4, close to 5 millimeters, and they are generated only due to thermal gradient. During the analysis of global structure, this expansion will lead to additional force to the other members. That's why we think that we need to use global structure simulation. At this presentation, I have just showed these two simple examples that will make this easy to understand, but we have already done this, used this methodology for bigger examples too. That's why we need an automated tool. So to point some conclusions, the main goal of this work was to provide a fire-thermo-mechanical interface model to performance-based analysis of structures under fire. The application cases showed verified that the proposed procedure can precisely evaluate this interface between CFD and FEM models. And the addition of the heat transfer coefficient distribution and the definition of this thermal exposure help to reproduce correctly the heat flux at the FEM model. This automated code, FTS to FTMI, which is now available at the FTS repository, was able to extract the variables from the FDS result file, the boundary files, and generate all the boundary conditions needed in answers by APDL scripts using solids and or shell elements. And the presented results demonstrated that this methodology can improve the reach of fire engineering, producing reliable performance-based analysis of structures under fire. So I would like to thank you all for the attention and end my presentation. Thank you.
Thank you, Julio. Time for a couple questions.
Hi, I'm Daniel Rosberg from WSP in Sweden. I really appreciated your talk. Thank you. Two questions for you. The first one is you showed us two cases of localized fires.
Yes.
Could you mention a few words about those fires in terms of width outside, number of solid angles, and so on, that we need to consider when using such methodology for this time process?
Well, in the first model, the simple panel, our grid size cell was about 5 centimeters, the size. And I think we used 2.5 centimeters in the second example, that is this 2 column. And what is the other question about?
Radiation model, for instance, the number of solid angles.
We used the radiation model inside of FDS.
So 104.
104.
Would that have a great impact on your result? Did you change that number?
Well, we didn't try to do that because we are focusing in the interface. Of course, if we change this number for a few, we will have impact, mainly if the radiative process is mandatory. For these localized fires, the heatest part of the structure will be handled by radiation because the fire is really close. So if you change this parameter, we will not have good results. We didn't try to do that, but that's what we expect.
My second question is, I don't see this difficult to you, but I would appreciate your comment on it. You showed us localized fires, design structures, mainly for fully developed fires. How do you think that would FDS, for example, have the capability, to give the input data to the model?
Yes. Actually, the simple models is better to have the first understanding. So if I show you one of our models in Brazil that we have an offshore structure of 50 meters for 70 meters and we have fire all over the structure, that would be hard to understand what's going on. But we have applied this model to big structures to see if we can handle global structure simulation, and we have good success.
Any other questions?
Yeah, very short one and very simple. Why don't we use for the both simulation for fire and the
Yeah, I have heard that a lot, but in the Fluent, the combustion model and everything is not done yet. So we have a lot of work to do in that field too. It's better, for our understanding, it's better to use all the FDS development all over these years to handle the fire simulation, better than Fluent or CFX.
Okay. Yeah, I see our fire simulation already done with Fluent.
I think it's just choose one, right?
One last question, and last time I used Fluent, it was really hard to use, but maybe it's gotten easier. I don't know.
Yes. At this,
Could I repeat the question so that, could you turn on the microphone so I could repeat the questions? I'm on? Okay, so the question was, you showed a forward calculation.
Yes.
You showed the FDS calculation giving temperatures to the structure. You did not then show the structure buckling and,
Yes.
and changing your temperature calculation.
yes, this work is really a one-way coupling. We have the results from FDS to ANSYS. And when I made this work, I was at the Federal University. Now I am guest researcher at NIST, and we are working now in this two-way coupling when we get the displacements and the surface temperature from a finite element method inside of the FDS simulation. So it's ongoing work.
Okay, well, thank you very much, Julio.
Thank you.
Appreciate it.